Hey, welcome to The Explainer. Today, we're tackling a really cool coding problem. How to find the wealthiest level in a binary tree. It sounds specific, right? But trust me, the technique we're going to learn is a total game changer for a ton of other problems too.
So how do we even think about this? Well, imagine a family tree, but instead of names, every person has a number representing, I don't know, their net worth. Our job, find the one generation, the one level that has the most money when you add it all up. Simple enough, right? Let's dive in and see how it's done.
Okay, so first things first. Before we start writing any code or even thinking about strategy, we have to be super clear on what we're actually trying to do. Let's lock in on the goal.
All right, so the goal actually has two key parts. The first part is pretty straightforward. We just add up the values for every single level in the tree. The second part, we find the biggest of those sums. But there's a little twist, a tiebreaker. If, say, level 2 and level 5 have the exact same maximum sum, the rules say we have to pick the one that's higher up in the tree, the one with the smaller level number. So in that case, level 2 would win. That's a crucial detail.
Talking about it is fine, but seeing it in action is way better. Let's walk through a couple of examples to make this whole thing totally concrete.
Okay, here's our first tree. Now, you'll often see trees represented like this, just as an array of numbers. It's a really common way to handle the input. That first number, the 1, that's the very top of our tree, the root.
So let's do the math here, level by level. Level 1 is easy, it's just the root, so the sum is 1. Then we go down to level 2. We've got a 7 and a 0. Add them up, and that's 7. Okay. And for level 3, we have a 7 and a -8, which gives us a sum of -1.
All right, so let's look at our sums. We've got 1, 7, and -1. The biggest one there is obviously 7. And where did that come from? That was level 2. So our answer is 2. Simple as that. Okay, that was a good warm-up. Let's try a trickier one.
Whoa, okay, this next one looks a little more intimidating, right? We've got bigger numbers, and you see those nulls in there. Don't let that throw you off. A null just means there's an empty spot, a missing branch on the tree. The core idea, the way we solve it, is exactly the same.
Let's just quickly run the numbers again. Level 1 is 989. Level 2 is just that one big node, 10,250. Level 3 adds up to 9,305. And level 4 is way down at -32,127. So if you compare all those, who's the winner? It's level 2 again with that big sum of 10,250.
Okay, so we get it. We know what we need to do. The real question is, how do we do it? And how do we do it efficiently? We need a solid strategy, a system for visiting every single node on one level before we even think about touching the next.
And this building analogy is seriously perfect for this. Think about it. You don't just walk into a building and take the elevator straight to the top floor. No, you have to explore it floor by floor. You check every room on the first floor, then you go up and check every room on the second floor, and so on. This methodical, level-by-level approach has a name in computer science, and it's a big one: breadth first search, or just BFS.
So here's our game plan. We're going to use something called a queue, which is really just a fancy to-do list, where the first thing you add is the first thing you do. Step 1, we add the root node to our list. Step 2, we go through and process everything currently on that list. That finishes off level 1. And here's the clever part. As we process each node, we add its kids to the end of the list. So naturally, they're all lined up, ready to be processed as the next level. It's a beautiful system.
All right, this is the part I love. Let's see how this great strategy we just came up with actually turns into real C++ code. We're going to go piece by piece, and you'll see how our game plan maps perfectly to what we're about to write.
First things first, we got to kick things off. We create our queue, that's our to-do list, and we push the root node onto it. Bam! The process has officially begun. Now, this part right here, this while loop, this is the engine of the whole operation. It's super simple. It just says, hey, as long as our to-do list isn't empty, keep the engine running. Once that list is finally empty, we know we've visited every last node in the entire tree. Job done.
Okay, pay close attention because this next line is the magic trick. It's the secret sauce of the whole algorithm. Right before we start looping through a level, we ask a simple question: how many items are in the queue right now? We store that number. Why? Because that number tells us exactly how many nodes are on the current level. This is how we draw a line in the sand and make sure we only process one floor of the building at a time.
And we use that size we just saved to control a for loop. This loop is going to run exactly that many times, no more, no less.
It guarantees we only touch the nodes that were part of that initial snapshot. Inside the loop, it's pretty routine. We pull a node off the front of the queue, add its value to our running total for the level, and then, super important, we add its children to the back of the queue. They'll just wait there patiently for the next turn.
So once that for loop is done, we have finished a level. Now it's time for a little bookkeeping. We take the sum we just calculated and ask, is this new sum bigger than the best one we've found so far? If the answer is yes, then we have a new champion. We throw out the old max sum, store this new one, and, of course, we make a note of the current level number.
And there you have it, a solution that works perfectly. But just having the answer isn't enough. The really valuable part is understanding why it works. So let's quickly recap the big ideas that make this whole BFS thing so elegant and powerful. It all comes down to a few key things working together beautifully. First, BFS is just tailor-made for any problem where you need to think level by level. Second, a queue, with its first-in, first-out rule, is the perfect data structure for BFS. And finally, that little trick of grabbing the queue's size before the inner loop, that's the linchpin. That's what holds it all together and lets us slice the tree up into perfect horizontal layers. Look, if there's only one thing you take away from this whole explainer, let it be this. That single line, int size equals q.size. That is the golden ticket. It's what elevates this from just a random walk through a tree to a very precise, level-aware algorithm. It creates a perfect boundary, letting us say, okay, stop. Finish this level completely before you even look at the next one.
And that pretty much wraps it up. You now have this incredibly powerful BFS pattern in your coding toolkit. So I'll leave you with a little challenge to think about. How would you tweak this exact same code not to find the max sum, but to find the widest level, the one with the most nodes, and then calculate the average value of that level? The solution is right there in the code we just wrote. Something to chew on. Thanks so much for joining us.